Yes, we are.
Awesome.
Thanks,
All
Julie.
right. Yeah, thanks everybody. So my name's Julie Winchester. I work with the Morphosource 3D data repository at Duke as the technical director alongside Doug Boyer, the founder and overall director, who unfortunately can't be here today. And I'm going to be talking a little bit about provisioning and sustaining storage of heavy, so that means like large file size image data in Morphosource. And I always like to start these talks with like a little detail about just what is Morphosource. It's a digital repository service at morphosource.org where researchers, museum curators, and the general public can find, download, and upload 3D media representing physical objects of academic interest. So mostly biological specimens. Just some basic facts and figures for Morphosource. We started in 2013. We are headquartered at Duke University in Durham, North Carolina, and we are largely financially supported by NSF grants and Duke commitments. And actually, we rebuilt the whole site in early 2021. Some basic numbers of the data holdings on the site. And I'm just really quick going to talk about sort of how does a digital repository like Morphosource that stores heavy data like CT or photogrammetry image stacks or 3D meshes, how do we store that data and preserve it for the long term? Specifically, I'm going to go into what are we currently doing for storage, and also how can we improve that in the future? And as part of that, so a little closer look at our data holdings. So you can see our breakdown of the media we are storing by media type, mostly meshes, then largely CT image series, and more 2D images than you might think, because we do allow 2D images in video. And in total, it's right around 76 terabytes, which is honestly less than you might think it would be. That's because most of the data on Morphosource that is contributed by users is sort of high-yield reusable data. And we think that that's sort of the power of carefully curating data for archival, that it's not just all data that could be archived, it's the data that amplifies the reuse potential while helping to save server space. And speaking of server space, how do we actually store the data? I'm not going to get too technical about this because really the approach we use right now is really simple. It's about the most basic you can. We use Fedora or FC repo as the sort of underlying binary file and metadata storage layer. And Fedora is pretty tightly, it expects there to be a local file system. So it's just like in any laptop or desktop where you have a local directory of files, you're putting files in the directory local file system. Fedora wants a file system like that. So through the Duke Office of Information Technology, they help us coordinate all this. We have an app server hooked up to like a network mounted file system where Fedora is just putting it right in the file directory. And this will become a little bit important a little later in the talk. We do backup that network file store. We have monthly snapshots. And all of the data is hot. So none of it is in cold storage. All of that data is immediately accessible, which does mean compared to something that might be more like a cold storage solution, it is relatively more expensive, which brings up the question, how are we funding the data right now? So Duke has helped us set up sort of an organizational service center that we use both to track costs from media deposits, but we also track incoming funds supplied primarily by NSF grants and Duke support. So right now we are subsidizing a significant proportion of contributed data. But we are also taking in funds from some projects with data storage budgets from grants. Now, we do expect over time that we're likely to require deposit fees for more users. And I will say this isn't a funding model talk, but I'm happy to talk more about this in later questions. What we have done working with the projects with funded data storage budgets is to develop a prepaid deposit fee model that we feel is very competitive with other storage solutions and is actually tuned to meet the specific needs of academic data projects. But like I said, we could talk more about that. But now I'm going to turn back to the actual storage, to specifically how our storage has grown from 2019 to present. So in the last few years, our storage has actually grown pretty linearly, adding 13.5 terabytes every year, which, because that's a nice linear line, we can go ahead and predict that forward maybe 5 years into the future. But for a number of reasons, that is likely to be a pretty conservative estimate, both because more scholarly communities will likely begin to use Morphosource, and also just because 3D scanning technologies are just getting more common every year. This table is just showing, basically reflecting what's on the graph on the right, sort of how much data we expect to have at the end of each year. And I bring it up because I want to talk a little bit about increases in storage costs. So right now for this year, we pay 0.17 cents per gigabyte per year, but we do expect that cost to go down a little bit every year. 8% is our current value that we use for our projections based on historical data. And using that, we can turn that 5-year estimated storage graph into a storage cost graph, which you can see that thanks to the decrease in storage prices, that line starts to flatten. But it still, produces by 2027, $16,500 a year in annual storage costs, which is just really to say that it's still a non-trivial amount that must be funded for that, which means that we have a strong incentive to reduce storage costs moving forward, both for the data sets that we are subsidizing and also for the grant-funded projects as well, because we want to be able to stretch the length of time we can store money based on those budgets. Fortunately, Duke IT actually got recently funded by NSF for a project that might help us. Before I go into that, I wanted to come back to this distinction between file system storage and, say, object storage, which is more like an Amazon S3, an Azure Blob. In object storage, instead of just storing files on a file system where the file could be anywhere, you instead park a group of files at a place, an object, which is usually like an HTTP URL that you can query to get the file or to get information about the file. And it tends to be a little more efficient and cheaper than direct file system storage. So Duke OIT was recently funded by NSF to build a system they're calling Fast Research Storage. They're using a piece of software called a Ceph storage cluster, which Ceph basically just allows you to bring a hardware cluster, a bunch of different individual machines, individual sort of storage hardware, to create a nuanced, tiered storage solution that could combine file system storage, you could combine it with object storage, and you could even combine it with object storage that has different tiers of speed. Maybe some tiers are a little bit slower to access data, and they're cheaper to store data in. Or you can connect the Ceph cloud to cloud storage, which means for data that is less frequently used, you could use this to sort of automatically tier those data into a slower or colder storage tier, which makes it cheaper. And therefore, you can use this to decrease your storage costs across the board. And some of the numbers we're seeing are that this could potentially reduce our data storage costs to 30 to 50% of the current rates. Or in other words, if we have a budgeted life for a data set of 1 year, it could extend that life up to 2 to 3 years. Got a couple more minutes. I will say, we're going to be moving Morphosource towards this model, which is not trivial. It is going to require some technical work in order to get to that point. I won't get too deeply into it, but there's a lot of upside to doing that work. And then, as I said, it will sort of promise to significantly reduce those costs of storage. And yet, although that will help, it will probably not fully address sort of next generational data challenges that are already happening. So this is just 3 different groups that we've been working with. So Doug gave a talk earlier today about how we've been working with collaborators at Harvard that are generating 300 terabytes of histological slide scan. We've been talking with Nelson and other collaborators of his about a project with Yale and other institutions to add 120 terabytes of data from a single photogrammetry project. And we've talked with the Natural History Museum in London, who project to produce over a petabyte of data for the next 4 years. When you start to get to those scales, even cheaper local storage, starts to become unpalatable in terms of the rates. And also, it's possible that these institutions, could make use of having their data discoverable in a central resource like Morphosource, but they could also potentially contribute local institutional resources. And I have more slides to go into these, but I'm just about running out of time. So I think I will round up here just to say that we have a number of different plans to help meet those diverse needs, from a solution that we call remote backed data, which is basically media records in Morphosource, where instead of us storing the binary file on our database, we instead connect that file up to a remote file store, say at Yale Institutional Storage, which that solution is likely to be most appropriate for projects of limited duration with large data archiving needs. We are also helping some institutions set up their own forks of Morphosource, separate Morphosource instances, where they're basically running a separate copy of the software, maybe to store their single institutional data. And eventually we will be able to basically have that data in an institution-specific instance reflected in the central service. And of course, we're always going to be supporting the Morphosource local prepaid storage that, especially as we move forward, as we add sort of automated tiering, we really do expect that to provide some of the most financially competitive and flexible storage solutions available for a centralized service like that. Yeah, and I think I will stop there. And
Julie, I'd just like to point out
yeah.
there are a few questions in the Q&A. I'm not sure if you want to take a look at those now or if you want to type answers, but you might want to take a look.
Yeah, real quick. Yeah, so cool. Yeah, so I see one of the questions got answered about the internal cost. Jason Bestard asked, do those storage costs include backup costs? Yes. So we maintain a full backup of all of our data, and we do snapshots daily for a month as well. Ed Stanley asked, do you expect the average size of data sets will increase over time? Maybe that's best. And maybe the other questions are best saved for the end, the Q&A discussion. I would expect average size of data sets to increase over time, but I might also expect people to come up with more community standards about what is the most high yield reusable data, which might also be a moderating influence on that. So I feel like it could go either way. But I think from there, I will stop sharing, and maybe we can sort of hold the rest of that for the Q&A afterwards. And I can yield the floor to whoever wants to give their talk next. I will call on someone if someone doesn't volunteer.
I could follow up if you like.
Awesome. Sounds good.
I think it fits with some of the things you said as well. So let me just get my screen ready.
Great.
Let me get it over here. All right. Let's see. Now let's share screen. Screen 2. Share. All right. So I'm going to talk a little bit about strategy for how we store our data and make it available to the broader world at the Yale Peabody Museum. Let's see. Slides. Nope. All right. So just to give a little background, at the Peabody Museum, we have a diverse set of collections. It's a lot more than just biodiversity collections. We have anthropology, Babylonian material, mineralogy. So things that are, outside of the scope of what would typically be what we're used to, things that fit into Darwin Core records. So that brings up some challenges right there. We have over 14 million specimens and artifacts, and over the past 10 years, there's been a major push in digitizing as much of it as possible, whether it's capturing metadata or doing 2D imaging, 3D imaging, CT scanning, you name it. A little bit about our traditional data store and kind of going along with Julie's model of there being these heavyweight assets versus these smaller weight assets. These are our small assets, which would be our media, our digital images, our videos. Even though videos themselves can be rather large, they're small in comparison to our CT scans and other 3D data sets. Audio and documents. Most of these data sets are images. We have roughly about 30 terabytes of storage for this information, but it's only about 13 terabytes of actual data. The rest are backups and derivatives of the stuff that are used for sharing. And you can see a little breakdown of which collections are producing the most amount of data. Invertebrate paleontology has quite the largest number of assets at the moment. We probably have about another 110,000 worth of images that are just sitting from TCN projects that we're waiting to ingest and get integrated with our system. And if you look at our growth graph, you can actually see the little drop around 2019, 2020, and that's kind of the impact of COVID, where not having students on campus to be engaged in a lot of the digitization projects have really slowed down some of the progress on getting things digitized. So the way our systems work, so we have our normal EMU catalog system, but all of our digital media go into two systems that are known as Preservica and NetX, and together they make up our digital asset management system. And Preservica represents the digital preservation system, which is where all the masters, the high resolution images get stored. And then NetX becomes more of like a front end that we can use to discover images. It hosts derivatives, smaller, lightweight versions of the masters, and it can give us access to the data that's in Preservica as well. And, so it's nice. Whoops, I have one slide that's, oh yeah. And so this here is a screenshot of what NetX looks like. So within NetX, we can, select images and create collections of stuff, and then we can actually share stuff to researchers. So I could sit here and make a collection of stuff that someone is interested in, and I could push it to somebody and say, here's a link, go download, these, images related to sturgeon or whatever. So there is that. One thing that our system does is everything is indexed across all of our different platforms that we're using, right? So the NetX stuff, the Preservica stuff, all of it feeds into something that is hosted on a IIIF server that makes our images available to a broad number of platforms. And so right here, you can see our screenshot of our data portal at the Peabody, and for all of the images, there's this link that says IIIF, and that allows us to visualize the images in this using standard protocols that the IIIF format has, or the IIIF standard has developed, and allows you to use various different browser or different browser tools to look at data from IIIF. And what's really nice is you can do more advanced things. So like here, you can do like deep zooming and looking at high resolution imagery, but you can also do things with using IIIF by creating unique collections, bringing collection sets together from different institutions, or annotating images, as in this case here, showing a moth that's being annotated, or a vase that has been unrolled and then annotated and transcribed. And so it gives you this kind of capacity to do these kinds of things. And then moving forward is we can take that same kind of data, and as part of a broader index, we're actually working right now to integrate across all of the collections at Yale, not just the Peabody alone, but the museums, galleries, and libraries, to bring everything together into a central discovery platform. And so this is pretty complicated because there's a lot of metadata reconciliation that has to happen across all the different groups that are out here, but it's still based on, a lot of it's based on having this common standard, IIIF, being able to get our image data into IIIF servers so that they can, the proper data can be generated so that we can share them across the various divisions. So now I'm just going to talk a little bit about our large heavyweight asset data storage. And so we currently have about 5,000 assets. Most of it is CT scans, but we also have some photogrammetry, multi-view image sets, 3D point clouds, some meshes, and other things in there as well. It's total about 15 terabytes of data storage, and it's all stored on a Wasabi backend. So Wasabi is a cloud-based storage, and so some of you may have heard what Julie had mentioned earlier about Amazon S3 as a storage. Wasabi is a Amazon compatible API that is identical to S3. You can use almost all the same S3 libraries that are out there and all the same tools related to S3. So if you wanted to, let's say, mount this cloud storage on your hard drive on your computer as just a local hard drive, you could do that. And then on top of that, we've built this tool called the ingester, which is an internal tool that we've built for pushing data into our Wasabi cloud storage. Now, these were tools that were built a number of years ago and was meant specifically to deal with these large object data sets. More recently, we've transitioned over to using Wasabi across all of the Peabody collections. And I think my slides may have been out of order, so I may have missed a slide. But one of the things is all of those lightweight assets were originally stored using an Amazon S3 backend, and we have since transitioned all of that to a Wasabi backend as well, as there is a Wasabi plugin for now for the Preservica data preservation system. And so with that, we can have a single process for doing that. And now we're in the process of migrating or developing the process so that we can migrate these large objects into that same backend. And that'll make it a lot easier so that there'll just be a single flow of data. The way it works right now for our heavyweight assets is we use that ingester app. So our ingester app connects to our EMU database so that we can get general metadata around the objects. And then from that, we can then take large, the heavyweight assets, whether they're shipped to us on hard drives or we've generated them locally, and then they get uploaded through the ingester to a temporary storage facility that we have that's called Storage at Yale. And that can have a number of different backends, but it's something we don't have to worry about. It's a Yale provided service storage that's provisioned. And then we also have processes where we can bulk upload. So if we do get that whole hard drive and we don't want to upload them one at a time, we can take that whole thing and we can upload it into this storage at Yale. And what that ingester does is it has all the zip files or the large, packages of data that need to be uploaded, but along with it, it generates this manifest. And this manifest tells us how we're going to store this thing. And it has all the metadata that we need that we want to bring back into our database. And so then that all gets pushed to Wasabi, which is a pretty straightforward thing. You're just using APIs like the same kind of APIs you would use if this was S3. But then we do another process where we then download the data back from Wasabi. And this is a validation step where we can check hashes, make sure the data is exactly as it was when it went up there and it's still usable. We actually open up the zip files and we check every file that's in the zip so that it's a very robust process. Once we get the green light, then we can take that metadata and then we link it back into our EMU server, and that's when it becomes available. And so what's really nice is any collection manager here can go into EMU, they can identify an object they want, they can highlight the link out of it, and then they can just send it to somebody and they can immediately go and download that link if that asset was made publicly available. We do have things that aren't publicly available for whatever reason. And also within that manifest process, people can sign off on saying, yes, this particular object has limitations and can't be shown to the public for whatever reason. And we'll still use Wasabi the Wasabi cloud storage, but we just set various different flags and permissions to make that data stay in a private realm, if you will. And so moving forward, what we're looking at, and Julie kind of mentioned this idea of this kind of remote back storage. And this is part of our lightning bug project that was recently funded, which is focused on photogrammetry, but it's also focused on other styles of imaging. And so it's still a work in progress. There's a lot of evolving as to the technologies we're going to use. But just to give you an idea of what we're kind of thinking of is that, at Yale, which is up at the top, the YPM, we're going to be using Wasabi as our backend data store, which we kind of already have the infrastructure for. Harvard, which is a collaborator in this project, they'll also be generating data. We still haven't quite figured out what they'll be using as their backend, but as the important part is that internally we'll be using most likely Globus to be transferring data amongst the key partners that need access to the data and need to be able to actually perform computational processes on the data. And then we'll be pushing the results of the imaging processes to Morphosource, but we're going to hopefully be able to leverage that remote back data store process. And so we'll send stuff off to Morphosource, but when users want to go and they say, oh, I want to download this TIFF stack or I want to download this multi-view image set, they'll be able to get that heavyweight asset directly from our Wasabi backend data store. And one thing I probably didn't mention is that, Julie mentioned this idea of hot storage and cold storage. Wasabi actually acts as our hot storage. It's publicly available, it's high speed, and so we haven't had any problems using it as live connected storage. And so that's kind of where we're at right now. And with that, I will look at the chat. So someone's asking terabyte per year cost. So the total cost per year is a little complicated because it's distributed amongst a number of different divisions, the way we handle our pricing model and who pays for what. But it's probably, if I had to estimate, we pay somewhere, I would say at most, with all backups included. And one thing I didn't mention, for everything that goes into Wasabi, we also have an Amazon Glacier backup. So that gives us, I think that was the slide that got messed up and out of order. That didn't mention, that talked about the Amazon Glacier backup and price, and that is a cold storage technology for us. And so price per terabyte, they're about equivalent, Wasabi versus Amazon Glacier. And I think total, if I had to estimate, it might be about $300 a month for the total that we use Peabody wide, including both the heavyweight and the lightweight assets. The heavyweight assets might be probably about half of that. Let's see if I can, I'm not good at keeping up with the chat question. Does anyone have experience actually recovering from Amazon Glacier? So I have never ever had to use it. I don't know if anyone else on the chat has ever had to go get something from Glacier. So how long does it take to transfer images from Wasabi to local hard disks? Are there costs involved in retrieving? So that's the other advantage of Wasabi, is there's no ingress or egress charges. And so that's, I'll admit, we don't have a lot of ingress and egress on our data right now. Most people access our data directly through Morphosource, right? They go download a CT scan. And so right now, Morphosource is taking a lot of that ingress and egress. Now, when this remote back storage starts happening, then yeah, we will be serving up the data directly. But with Wasabi, there is no cost in that. So that's another advantage of using them. Where if you're using Amazon S3, there is a charge for access to data. And as far as performance-wise, I mean, I don't have raw numbers. I mean, most of our access, it's all scripted stuff. So, you know, things are being pushed around the clock to Wasabi. You know, it's just as fast as anything else, you know, that you know, I haven't noticed any, like, it's a major problem to download data or to push data to them. All right, doesn't look like there are any more questions. So who wants to go next?
Well, I can go, or I think the other talk was on Symbiota, so either way works for me. Okay, all right, so let me just get set up here. Whoops, but I'm not, sorry, you can't see my screen. Let me see if I can try that again. Okay, so I think you can see my screen. Let me see if I can throw this into presentation mode. All right, can you see my title card here? Okay, cool, thank you. So hello, my name is Michelle Koo. I'm from the Museum of Vertebrate Zoology at UC Berkeley. I'm also part of the executive committee for the Arctos Working Group. So I'm going to be talking about Arctos and linking media in our collaborative collection management system, which fully supports extended specimen network. So we see this as just part of the regular sort of work that we have to do when you're managing any collection. So like you were seeing with Yale, we host actually a lot of different kinds of media. So it's we're a collaborative system for about 50 organizations right now. And generally we consider media to be anything that you can attach to an object or other tables to help visualize or document that. So that could be PDFs, TIFFs of field notes, obviously CT scans, SEMs, you know, audio, video, and all sorts of other photographs that are either, scanned or born digital. But right now I'm going to focus only on the things that are relevant to basically the overt project. So just a couple of little technical details. So Arctos is hosted at the Texas Advanced Computing Center. So TAC actually houses our storage options as well. But we also have a lot of flexibility. So many of our users also use their own local university-based cloud servers. And I will show you how we link to third-party repositories like Morphosource. And so media then can be linked to objects, agents, in other words, people like collectors or creators, transactions like loans, accessions, even taxa. We also upload PDFs of publications, and images can be associated to localities and events automatically through the right metadata properties. So the ones that I'm going to focus here will be about the CT scans and our 2D images and our 3D images right now. And these are all basically products from a number of grants and projects like Overt. So what's been really exciting is to see these linkages where we can have a CT scan as well as the 2D images of the same specimen and being able to have those all discoverable. So we have a little bit of legacy TC scans from before the NSF award. And so we've also had to figure out how to deal with those at a local basis. So these are not actually on Morphosource right now, and they may not be because they're actually their resolution is quite different. But our most common kind are the photographs, and these are becoming much more frequent and just a sort of a matter of our course. Sometimes people don't even have PDFs of documents; they'll just take a picture. So we support TIFFs, JPEGs, and RAW formats. And then, of course, we're starting to have a growing number of 3D images. So these can be linked in a number of ways. There's basically, I would say, 3 general different ways that Arctos handles these kinds of images. So they can be something linked to an external repository like an identifier. So Morphosource, for instance, in this example, you'll see this cat-eyed snake has a Morphosource specimen ID number, which would then take you to the Morphosource page. And that would show all the various digital objects that particular specimen has uploaded to Morphosource. And in this case, there's 2 media objects. Both of those have been minted at their own DOIs by Morphosource as ARCs, and we link to those as well. So that's one method. If there's 2D images, those would eventually show up because there's this community aspect to Morphosource where other researchers may have uploaded scans that we don't really have maybe awareness or control over. These would show up on our specimen ID page if the metadata are uploaded correctly, or we bug Julie and Doug to help us sort those problems out. We can also link the photos and 3D images, as well as these CT scans as media objects, and those are then linked directly to any specific specimen. So in this case, for this cat-eyed snake, you can see it has a number of media objects. There's some photos, there's a CT scan, and then there's also a 3D model as well. This just happened this week where Arctos will start has set up a bot to ping the Morphosource API, so we can actually retrieve those Morphosource DOIs and specimen IDs automatically as we find them with our known Arctos institutions institution codes. So that will take off a lot of the burden on curators to actually go and find or be in communication perhaps with researchers who are uploading digital assets that, you know, again, we may not be aware of or have control over. So this bot will help us keep links up to date. And lastly, I just want to mention that Arctos also can treat media as records itself. Arctos also has a number of cultural and art collections. And so here's just a fun excuse to show off the Three Musketeers. So here we have, it's media that's also media. So in the old days, one of the mediums might be paint. So here's a painting. There's also photos of it. So these are actually its own record. I mean, there's pluses and minuses, I should say, with all of those things, which we can discuss in the Q&A as well. So one of the other aspects of Arctos, if you heard Emily Breaker's talk, she mentioned projects. So those projects are these internal web pages that gather all the assets around a particular theme or transaction. So in our case, we created, of course, Arctos projects for a number of these awards. So this is the one for Overt. It's got a description, some nice graphics, but it also keeps up a dynamic list of all the records that were sent out for scanning at our other Overt partner scanning centers or internally. And it also keeps track of those particular specimens and where they came from, the other projects basically that originated these specimens. And I just wanted to point out that so far, the Overt one, you can see that the specimens that are being used in Overt span a century, and they come from expeditions from around the world. So talk about reuse. Another related Overt project is OMESA. It's a pen. It focuses on Mesoamerican amphibians and reptiles. And this pen also includes 2D imagery of all the specimens that are being scanned. And in this example, I just wanted to point out Arctos is being able to link the cross-institutional specimens that are contributing to this particular project. But again, you can see in the gallery that's growing, you can actually either browse through all the media that's here linked to either Morphosource or to tax storage where you could download the images directly or have them surface as a search result. And lastly, this is just an example from the University of Wyoming. They had a 3D model exhibit. All of their imagery ended up as 3D models on the interactive website Sketchfab. And so Beth Womack, the curator there, had all of their media links linked directly to Sketchfab. And she also did include the Arctos database link. So there's a little reciprocity there. But of course, this is a commercial site, and this doesn't store the image directly, but at least gives you users and the public access to where these assets may reside elsewhere on the internet. So that's about all I've got for here, and I'm open to answering or discussing any questions. It's like I said, we're kind of making this up as we go along. So thank you very much.
Should I go next? Can you see my screen okay?
Yeah.
All right. Thank you, everybody. Thank you for organizing this. Also, thanks to Dave Blackburn. Some really excellent talks. My voice is so I'm recovering from a bit of a flu. So I'll be talking to you about long-term image storage and accessibility for the IDIC-Bio Symbiota Support Hub. This is a joint presentation by the Symbiota Support Hub team. Greg Post is also one of the co-panelists who can help with some of the Q&A if and when we get there. This talk is maybe just a little different in terms of flavor because our mission is, very outward facing towards all of the collections that currently use Symbiota and are currently in forward projecting communities for which image hosting and publishing will have to be provided. And so the talk is not very technical. It does reflect more of a sort of strategic and community type perspective. So I do want to take this slide just to introduce and acknowledge the Symbiota Support Hub team. We've built a wonderful team here, and we have quite a presence of which I'm proud and feel fortunate. So this includes Ed Gilbert and Jen Yost as part of the lead team, but then we have our core, including Katie, who's both data and project manager, Greg Post, who's our IT and systems administrator, Lindsay Walker, who's community management, Laura Prado, who is a biodiversity informatician in addition to Ed, and also Samantha Oriana, who's doing a lot of our international community outreach and coordination. In terms of the scope and resources of the Symbiota Support Hub presently, here are some high-level metrics, and in fact, they're not all from 2022. But as you likely know, Symbiota sustains these self-forming, self-identifying, self-evolving themed portals, of which we are currently aware of 46. This encompasses more than 1,500 natural history collections, of which I believe slightly more than half or around half are live managed, and amounting to some 80+ million occurrences. And as of 2 years ago, we actually have not done this very recently, more than 24 million images that are being accessible through the Symbiota portals, but of those 9.6, again, about 2 years ago, actually pertain to live managed Symbiota collections, meaning that we host them on our IT infrastructure. Speaking of that infrastructure, we are going with a fee-based internal service with ASU Research Computing, and for internal users, the fees are actually publicly available. I did paste them into one of the answers or questions that were posed by Jurid about this. And we currently operate 5 virtually managed servers. With this service, a total of 36 cores and 136 gigabyte of RAM. We have a high bandwidth connection to the internet, and our current total is about 16 terabyte of image assets, which is at this cost linearly expandable, as are these various stats. This is more about understanding what our mandate is, what is in scope versus beyond scope in the context of the current IDIC-Bio 3 2021 to 2026 Symbiota Support Hub funding period, which is important because it relates to sustainability considerations that will come later on. And so our current scope actually is a two-prong support provisioning. We are to provide up to 30 terabytes in image hosting capacity for the duration of this particular project, and somewhat narrowly, if I wanted to say so, to those communities that are NSF, TC, and Symbiota portals that were initiated in 2020 or before. Okay, this scope includes quote unquote archival, so very, very large images, legacy image collections of larger institutions, backups, and also digital asset management system type of storage. We also have some complementary funding to be continuing the support of image hosting and serving for select existing Symbiota portals through the Cyverse infrastructure and services at the University of Arizona. Just a little bit on this, I didn't have very detailed workflow on services that we provide to Symbiota portal collections from their perspectives. And I might jump a little bit in and out because all I did here is I basically screenshot a couple of kinds of services. One of the things that we've been able to build up in the last year plus that is very valuable is Symbiota docs. And so as a first, and in many cases, ultimate sort of place to start and stop, to learn about how to interact in the context of image uploading and modifying and updating with Symbiota support portals. The docs would be the proper place to do it. We also have a Symbiota support group that provides regular monthly or so seminars. And earlier this year, there was a particular one here just about getting images into Symbiota portals. And I stopped at a random place.
Settings that I would need to set. One of these is a pattern match term. And so that's going to...
Just to illustrate the point that at this juncture, we have abundant collections manager or collections user and contributor friendly resources available to basically capacitate and move along users of these portals in the context of operating the workflows that are available and future workflows that will become available. So I have these two links here. There's also a help desk that we, of course, operate. So the short version here is, I'm not going to go into a lot of detail of the workflows, but there's a lot of support that we provide online. For example, this is just a snapshot of or a slide screen capture from the talk that Katie Pearson gave in February, alluding to the different ways in which Symbiota portals can access images, either externally by an institutional server, and we've heard example of this, or a cloud-based service, we've heard example of that, or through our system, or through Cyverse. And most of us will know that a service that was offered to Symbiota portals by IDIC Bio was phased out and largely transitioned to ASU a couple of years ago. In terms of what we feel our strengths are, and also the future direction in which we want to most incentivize sort of use, Symbiota focuses almost exclusively on web-ready image assets. So these are basically smaller JPEG type images or so, and particularly incentivized for live managed collections and occurrences. So that is the thing that we would at no time really want to be charging any sort of fees for, because that's what we feel is the service that's very important to the core focal academic communities that we serve. Symbiota is also strong at linking occurrences to externally hosted image assets in terms of attaching multiple images to a single occurrence record and managing observation images of the kind that you would also, for example, deposit with iNaturalist. So I'm not going to go much into detail here, but one of the functions exemplified and high level described that Symbiota portals offer and that the hub offers in terms of external hosting of images is there's an automated batch processing a tool. It's the one that Katie describes in the video that I very briefly played for importing both the records and then images. It supports CSV and tab delimited import. You can likely read some of these parts here. If you provide a catalog number, there can be scraping of HTML folder lists. There's a thumbnail building tool, derivative images, moving image assets to a web accessible location, generating storage, storing the URLs, and then associating with them with the occurrence records. All of this is automated, and then updates to those occurrence image linkages can also be facilitated via Darwin Core and IPT formats. In terms of the images that we directly host at ASU, just a few tenets there. So we utilize rsync and secure copy in order to move them across servers. Currently supported image transport or accessioning platforms include Secure FTP, Google Drive, and Globus. But we are, and this is a bit of a trope, very actively looking at Dropbox and OneDrive. So we have, in some cases, prototyping activities going on, and we'll eventually also move to Amazon Web Service compatible cloud storage system, and Nelson mentioned one in his talk previously. We are aiming in the near future to provide support for interacting with digital asset management systems, which is not the same as actually directly ingesting and sort of hosting them. That's not going to be our future. And we are strongly considering a IIIF image server to add and facilitate and wrap around and integrate with these various options. And we can talk more about that. So then just finally to close out, and thanks for sticking around, plans, constraints, and trade-offs. This is relatively short and sweet. So for the in-scope live managed collections in the context of IDIC Bio 3, our aim is to provide essentially continued growing and permanent support. But because of the mandate that we have, and this is a little bit of just being responsible as a community, there is therefore also other clients. So for example, if you get a grant that involves digitization, but it's not necessarily the capacity or a TCN type of project, or if your TCN started post the beginning of IDIC Bio 3, or if you're a government entity, or you're a private entity, or you might be an international entity or so, we need to think about ways in which we can implement a flexible, sustainable, transparent, multi-tiered pricing structure loosely along the lines of pay what you can. And so this also means that there is going to be some measure of cross subsidization going on, funds flowing from here in a sense to be able to keep the lights on and grow that part. And all of that is actually currently in development, but it started very recently, and it's part of the overall sustainability plan for the Symbiota Support Hub. So our intention is that we want to offer widely available web accessible image services facing as far outward as the IDIC Bio community and beyond is sort of suitable and willing to access us. But we also need to therefore build a successful, meaning competitive in terms of the pricing, also reliable and ultimately scalable business model in order to provide those services. And we've seen some examples in the talks today, and I think those make for interesting discussions. Constraints. So there have been questions about what it costs to have a terabyte of image storage per year hosted there and here. And frankly, as PI of the Symbiota Support Hub, I don't think about image hosting like that at all. I am sort of open to telling you that in the context of IDIC Bio 3 for ASU and the Symbiota Support Hub, our annual operating budget, including our salaries and our employee-related incomes and our indirect costs, hovers around 500K. Of that, less than 2% are terabytes and server fees, right? So if we continue to think about costs as a community commodity, as things that you can just pay a fee for, but we're not managing this correctly. I think we have to think about image hosting as a function of recruiting and retaining and generating prosperous careers for our specialized high functioning team members that can provide those kinds of services. And so the simple pass-through fees likely are scalable given the scope that we have and the scope that we don't have. I think they're likely very economically appealing if you just look at the sticker price of cloud-based services. But at the same time, that's not really the way to go about this as a competent sort of business management team and business design team, right? Future fee-based services to various indicated clients will need to partially offset also the costs to actually retain the team. And then finally, our current model purposefully does not include or address large archival images or large legacy holdings by large institutions that have created these. It also does not alleviate, of course, the need for more national and international prioritization and coordination of this issue, which has been one that we have come less together, I would claim, than on many other issues related to digitizing occurrences. And this is just a couple of links for further information. And thank you very much.
Wow, folks, that was very informative. And I thank you for pulling that together. That was wonderful. We actually only have 2 minutes. There's not a ton of time for discussion. I don't know if there's any question, Julie, maybe that you think would be a good one to pull out as kind of one question we could address right now, and then maybe the other questions could be answered in the chat or in the text.
Yeah, one thing I'll call out is Jason had pointed out, I think very accurately, that a big pain point for digitization is the storage of sort of raw or DNG archival files that may not be publicly accessible. The institutional storage solutions that may be available at larger academic institutions aren't always available to all TCNs hoping for a sustainable community solution. I think it's a great point. I think it's something to continue thinking about. I mean, we're definitely, I think for some of this, I do believe that Morphosource is trying to be a kind of sustainable community solution for some of these things, but there's always the question of how do we keep community sponsored resources sustainable, where institutional resources permit. That's why where we're trying to go with some of the remote backed storage, linking institutionally available storage up to a central community resource, like Nelson talked about, and like I talked about. But if that's not available, it's still something we really have to figure it out. So I think it's a great point.
Thank you all so much. I have to stop you for our next presentation. I really appreciate you guys so much and all of your talks. If you could type, it looks like Michelle right now is typing some answers, but if you are available to answer the questions that are in the Q&A, it would be much appreciated. And so up next, we have GBIF, ALA, IDIG-Bio, aligning systems to benefit data mobilization. And I'm gonna start by turning the mic over to Maureen Kelly, who works for IDIG-Bio at ASIS. Maureen, are you planning on sharing Javier's recording? Do you want me to be prepared to share that?
I have a recording and I think I'll try to just play it.
Okay, when you do play it, Make sure when you go to share your screen that you click the share sound in the bottom left when you're choosing the window to play your presentation. And that's what will allow the presentation sound to be played for all of us.
Okay, let's try this.
Maureen, I think that the right order of presentation should be that I should present first. Because I'm going to talk about the first phase of the collaboration, then it's going to be the Javier's recording, and then you.
Okay,
Is that okay?
sure.
Should I start right away?
Yeah.
Okay.
Hmm.
Just 1 minute here. Just a little bit of excuse for myself. I'm recovering from a flu, so if I go on mute, I'm still here. It's just that I don't want to hear you, that you hear me coughing. So that's going to be the reason. Okay, so I'm going to start. So as I mentioned, we're going to have the 3 presentations. The presentations are going to be the coloration around the GBIF pipelines. The first presentation is going to be me talking about the history of pipelines, what GBIF pipelines is. And then we're going to see the Javier presentation, and then the IT Bio team are going to present the future plans around the data pipelines. Okay. So what is it, the GBIF pipelines? The GBIF pipelines is more than a software component. It's more than a framework. It's an infrastructure that compromises a family of systems, services, and processes to manage the occurrence data. In particular, is composed of a set of crawling services to retrieve data from external sources like IPTs, Darwin Core Archive, hosted Darwin Core Archives, but also from let's say legacy XML protocols like, not all of them are legacy, like BioCase, Digger, and Tapier. It also implements a group of services to perform the data validation prior the data ingestion, and also collects metadata related to the data set being ingested, and also has several dimensions of interpretation of occurrence data. So once that data is validated, is storing multiple persistent storage like relational databases, file systems, cloud file systems, search engines, and so on. As complementary to that, there's an additional service layer to facilitate the monitoring, diagnosing, and troubleshooting of data ingestion and jobs that I'm going to show later. An important part of that infrastructure is also the dedicated staffing team that is basically doing the maintenance of the software components, but also the help desk to different data publishers. GBIF pipelines relies on other services and components of the GBIF infrastructure. Specifically uses the GBIF registry to retrieve information about the datasets, technical installations where the datasets are hosted. For example, the information about context also of datasets, and has a two-way integration with the GBIF dataset by synchronizing metadata from the different endpoints. It also integrates with the GBIF vocabulary service. That is basically a registry of control vocabularies used for terms that we found in GBIF mediated data. That's an ongoing work that we maintain here at the GBIF Secretariat. So far, pipelines have integrated some Darwin Core terms that are maintained in the vocabulary service. So far, we have a degree of establishment, the life stage, establishment means, pathways, and event type, which is going to be touched in the next presentation. But however, this is an ongoing work, and there are plans for future integration with more terms into the pipeline. Also integrates with the GR cycle, that is the global registry for scientific collections. That is a community effort to improve data around institutions, collections, and associated staff members. Worth mentioning that there's a previous success story with with IDBio. Now IDBio imports all the collections, the data into GeoCycle, and is now using the registry facilities and the registry interfaces to query to maintain that data. A complementary and supporting solution is called the history service, and that basically provides all the mechanisms to actually track the progress of the data ingestion jobs, and also to execute the jobs in the GB pipelines. Additionally, the pipelines infrastructure uses a battery of GB services. I'm mentioning here only two of them that were the most used. There are the species, the name matching the geocode for the reverse geocoding services. All these services that are here, the GB registry, vocabulary, GeoCycle, and the history service can actually be accessed and managed to the GB registry console that I'm going to show in the next slide. So,
Federico, I've been trying to ask in the background. We can't see any presentation. We just see you.
That is very embarrassing. Sorry.
I'm sorry. I should have piped in at the beginning. I was trying to find out behind the scenes if this was what we were supposed to be seeing.
Oh, yeah. No, that's not so. Can you see it now?
Yes.
Okay, so thank you. Sorry for the mistake.
Wait, no, this is your note page. This is not the presentation.
Show here.
Perfect.
Perfect. I'm gonna go back. Okay.
Okay.
Sorry for the mistake. I was rehearsing this. Okay. Okay, now we're ready. Okay, so I'm gonna rewind. So I'm gonna talk a bit about what GB Finance is, and a bit of the history of the GB Finance, and a bit of the history of the collaboration that we have with ALA. Okay, as I mentioned before, the GB Finance is not only a software component library. Is basically an infrastructure that basically compromises a family of systems, services, and process to handle and manage occurrence data. In particular, it has a set of crawling services to retrieve data from external services like IPT, Darwin Core Archives, and XML protocols like the BioCase, Digger, and Tapio. It also implements a group of services to perform the data validation, to synchronize the metadata, to collect metadata from different endpoints. And once the data is validated, it has a complementary services to actually to store that data in different persistent storages like relational databases, file systems, and search engines that are used later by the GBIF API. Complementary services are also provided to actually monitor and track the process of those data ingestion jobs, and also that plan provides the functionalities to trigger and to schedule the data ingestion tasks. An important part of this infrastructure, as I mentioned, is that there's a dedicated staff like the GBIF informatics group that is dedicated to support and maintain the infrastructure and the software components, but also the help desk staff that is there to assist data publishers in different questions and troubleshooting. So the GBIF pipeline integrates with different systems and components inside the GBIF platform. In particular, integrates with the GBIF registry to retrieve the information about the datasets, where the dataset is hosted. It also retrieves information about the contact information of the dataset, and that information is synchronized into the registry database after each data ingestion job. It also uses the GBIF vocabulary, which is a registry control vocabularies used for terms that we frequently see in the GBIF mediated data. As I mentioned before, some of the Darwin core terms that have been curated so far in the GBIF vocabulary and that are integrated in the GBIF pipelines are degree of establishment, life stage establishment, means, pathway, and event type, which is being used by the work that Javier is going to explain later. It also integrates with the GR cycle, with the Global Registry Scientific Collection. That is basically a community effort to improve the data on institutions, collections, and staff members associated to those institutions and collections. As I said, we're mentioning here that IDIC Bio has imported all the collections data into GR cycle and are now using the GBIF functionalities and web consoles to handle collections data. The history service is a supporting solution basically to facilitate the track to track the progress of the data ingestion jobs, and also to diagnose issues by the help desk staff in GBIF. The data ingestion platform uses a set of satellite services and components. I'm just mentioning here two of them. That is the species name match and the geocode reverse service that I use to interpret the taxonomic data and location data. The GBIF registry, the vocabulary, and the GR cycle and the history service are all accessible through the web application that is called the GBIF registry web console. This time I'm going to show in the next slide. Okay, here I'm showing just 1 second here. I'm showing basically what you can see here is this data set. For this data set, we're seeing the history of all the data ingestion jobs that have been triggered in the past. It also has the functionality here to trigger and to schedule the data ingestion jobs from here, and it facilitates also the monitoring of different running jobs. So if, as I mentioned before, from here we can manage information about the GR cycle collections and also the GBIF vocabularies. One second, I hit the wrong button. Yeah. Okay, bit more into detail with the data ingestion workflow. So basically, everything starts by downloading and getting the information of a data set that is being done by the crawling components. In this case, let's say, for example, that we have a Darwin core archive. That Darwin core archive needs to be unzipped. Once that archive is uncompressed, basically we run a set of validation routines that are going to produce a a set of Abro files. I'm gonna in the context of the GBIF pipeline, Abro is gonna be is used as the data serialization mechanism for all the intermediate tasks in the data pipeline. In this case, the Darwin Core Archive representation is transformed into this data format, which is later used by the interpretation routines. In this case, we use the Abro representation from the Darwin Core Archive, and we execute a set of parallel tasks to produce the information that is later being fed into the data warehouses. So all these interpretation routines are implemented in a framework that is called Apache Beam, that basically provides a unified programming model for data ingestion pipelines. And Apache Beam delegates this execution to a different engine. In our case, we use Apache Spark as the distributed data processing platform. Once this interpretation and data cleaning routines are finished, all those intermediate outputs are generated to actually to feed the data that we need for the different persistent storage. In this case, for example, we create a set of files for our data warehouse that is being used to support the GBIF download functionality. We create a record by record representation. Let's say the initial representation as provided by the source, and we store that information in a columnar database called HBase. We store some of the validation metrics that we created during the validation process. We store that information into a relational database, and then we also create a search index that is later being used by the GBIF API backends. Okay. The ALA ingestion workflow, if you can see here, is very, very similar to the GBIF ingestion workflow. In particular, the core components that I'm highlighting here are conceptually the same. In this case, they use a different set of technologies at the end. For example, for the crawling and for the job scaling, they use Jenkins plus other technologies. But the ingestion pipeline itself basically is implemented in using the same technologies that we have in pipeline. At the end, the ALA produces a different set of output files for their own usages. In this case, I'm highlighting that, for example, they use Solr that is different to the Elasticsearch one that we use to provide to support the current search APIs, for example. So a bit of the history of the GBIF pipelines and the interaction that we have had with ALA. The first approach, the first time that we met to talk about a joint collaboration was in September 2017. That was in the Natural History Museum. That was basically a meeting basically to share experiences and to share expectations about the different and approaches about the different data platforms that we were operating. It was in April 2018 when the GBIF informatics started developing the new version of the data ingestion platform that is now called Pipelines. That was an effort that was done by 3 developers and myself. And it was in December 2018 when we went into production with the first version of this system. At that time, we went in something that is called the parallel production. Basically, we were running the old ingestion platform plus the pipelines ingestion platform just to validate correctness, the performance and reliability of the new infrastructure. We went on holidays, and it was in January 2019 that we went to production. We switched off the old system, and we kept running pipelines since then. Not to not too late after that, we had a workshop in Australia, in Canberra. In that workshop, basically we dedicated more time trying to understand the specific requirements of ALA, the specific goals for implementing GBIF pipelines in the context of ALA, and also we provided some training around Apache Beam for a large group of developers in ALA, for the ALA staff. So the joint development that actually started by September 2019, and by setting the goals and unifying the programming practices and components. And ALA went in production with the pipeline, and was around April 2020. And the new, that's when the first phase of collaboration finished. And it was by April of this year that we started the second phase that we're going to hear more about it in the Javier's presentation. Some of the results of that collaboration, we have a closer coordination. We have a very frequent and open and honest communication. Basically, we have had weekly meetings and exchange of different situations during the development of this first and second phase. We have a transfer of knowledge in both ways. For example, in the way that we now process, for example, the geographic services, and the way that we are trying to bring more stability into IDs is heavily inspired on ALA. And ALA has also adopted some of the GBIF, the software development practices, and some of the infrastructure practices too. One result is also that we have a good standardization of practice and technologies around the common components that we have developed. We have a strong set of core components now that have been stable for quite a few time. And worth mentioning that in the case of ALA, there's been a substantial reduction in the Amazon Web Service cloud bill. That now that after pilot they managed to get rid of some of the technologies. Some of the challenges that we have faced. Both things we operate in different approaches. For example, GBIF, we operate an infrastructure, and ALA moves more in a project fashion. So that means that they have stronger deadlines than we have in GBIF. But we have the pressure of operating a platform that has to provide services worldwide. And also, we are talking about different dimensions of data. So we have to deal with more with a larger set of data sets, with a larger set of with a larger amount of data. But ALA have to deal with richer data in particular. We have faced changes in the team structures. We are both small teams, and something the priority changes, and we have to move the people from the pipeline development to different tasks, and we have had to accommodate that. We also had to accommodate different approaches to technology. So we are not using the same stack of technology to provide all the backend services for the APIs, for example. And one last thing, we have to recognize that the time zones and COVID imposed some restrictions on how to collaborate. It was like a few months back that we planned to have a workshop all together, and it was basically impossible because of the crowd restrictions and yeah. But yeah, in general, that has been a positive outcome. What is coming work in GBIF pipelines? It's been a while. I mean, since we started developing this 2017, this generation of this ingestion platform, we have accumulated some complexity in some of the components, and now we have started a process to actually to redesign the main components in a way that allows us to release software more frequently, and that allows us also to have a better collaboration with external teams. We are going also to a major upgrade of technology. It's not only the components that we use for pipelines, but it's also all the clustering technologies that we use for in GBIF, all the clustering, for all the computational resources that we use, that we have to undergo to a major update on that. We're trying to mature our process around how to collaborate with external teams, and we would like to grow the pool of contributors that are actively maintaining the main pipelines component. That's Javier is going to mention a little bit about this, but we also are keen to explore new technologies that we can include in the technology stack of pipelines to process different types of data. In particular, now that GBIF is initiating the work around the new data models that are basically richer data models that are not restricted by the Darwin Core Archive star schema. And finally, we also are aware that we need to improve the documentation around the pipelines and the main components and how the pipelines works. It is very common that we have questions of people asking how the different specific stages in pipeline work. For example, the name matching against the GBIF backbone, or how do we look up in institution codes from year cycle and that kind of features. So we need to improve that documentation for the general understanding and usage of the pipelines project. And so yeah, so that's it. Just one more thing here is that there is going to appear here. This is the group that has been collaborating so far. It is sorted in a way that the developer with most of the commits appears first, and that's by far my colleague Nikolai Bulik, who has been doing the main development for all the pipelines components. So yeah, thank you.
Thank you very much, Faye. That's very instructive. So, Javier, are you up next? You're muted. You want me to play yours, right?
Yes, he does.
Okay. Happy to do it.
Make sure you hit the share sound.
Maybe I'll make you do it.
Hello, my name is Javier Molina, Project Manager in the Atlas of Living Australia, ALA. I'd like to start by acknowledging the Aboriginal and Torres Strait Islander people as the traditional custodians of the land across Australia. I pay my respect to their elders, past and present. During this presentation, I'm going to show you the work that the ALA, in collaboration with the Global Biodiversity Information Facility, GBIF, produced for the Extended Data Model project. This is what we are going to cover. Let's begin. The ALA is Australia's biodiversity database and digital infrastructure, aggregating occurrence records for plants, animals, and fungi from across Australia. The ALA is a one-stop shop for Australia's researchers and decision makers to access trusted biodiversity data and services. The focus of this presentation will be about enabling new data types and the systems that support that. What's the problem being addressed? The ALA currently hosts more than 113 million occurrence records. An occurrence record answers the basic questions of what organism was seen at what location and time, possibly who observed it. The occurrence model has helped us, and it is not going away, but there is a limit to the types of questions that can be answered. We are missing, for example, the ability to get a set of comparable records, same methodology, same location, same efforts, to name a few. Expanding our data model to include events and better capturing absences is the first step to enable richer statistical models. In doing that, we will no longer treat occurrences in isolation. So we started the ALA Extended Data Model project back in January this year. What we mean by extended data is activity or event-based biodiversity data such as ecological surveys, expeditions, transects, bioblitzes. Darwin Core collectively refers to these activities as events, and this is a term that I'm going to use for the rest of the presentation. What we set to do was expand our existing systems. Our entry point is still a Darwin Core archive, but we are using event as a core, keeping relationships between events and relationships between occurrences and events. We wanted to use our existing systems, including BioCage Hub and BioCage Service, but they have incurred substantial technical debt and they were holding us back. So what we did about it? Rather than reinventing the wheel, we started a new collaboration with GBIF. We worked back in 2020 and 2021 with GBIF implementing the GBIF pipelines in the ALA, which was a success. We could tap into the expertise from both organizations. GBIF was and continues working on the GBIF Diversified Data Model, seeking to solve a similar problem, expanding their data model beyond occurrences only. GBIF had already been taking the lead in developing a refreshed user interface with up-to-date technologies. We wanted to keep consistent interpretations, contribute to the base GBIF pipelines instead of adding ALA-specific extensions. So how our original vision changed? We left our occurrence processing systems untouched, shown at the bottom of the diagram. We still reused the pipelines implementations, adding extensions to process events. This time, however, we commissioned a new ingestion deployment using AWS EMR, Amazon Cloud version of Spark. We used Elasticsearch instead of Solr to store a new event index. Elasticsearch, as opposed to Solr, allows to nest objects in the index. We also adopted GraphQL and React.js components developed originally by GBIF. And this takes us to what we produced. We built a simple but powerful data model around Darwin Core, having events as the central entity. We can represent events in a hierarchy and link occurrence records to an event activity. Particularly for the management of measurements and facts associated to either events or occurrences, we use the ENVData extension developed by the Ocean Biodiversity Information System, OBIS. By capturing methods associated to perform an activity, we can better represent absences. Think about the scenario of, I went looking for this particular species in this area, but I couldn't find it. We proposed extensions to Darwin Core standard. We developed a vocabulary of event types such as expedition or site visit. We also added an event name term. We developed additional GBIF pipelines interpretations for processing events, extending the existing interpretations for occurrence records. We also developed a new event-based user interface and download service. Finally, to start acquiring more datasets, we prepared a step-by-step guide and scripts that allow data providers to create Darwin Core archives with event information suitable for the new event system. All of the work that we produced was not necessarily smooth, but it is worth reflecting on it. The list is not exhaustive, but rather captures the most relevant points. Two separate teams meant to be subject to unavailability of staff due to competing priorities for their respective organization. Apache Spark is the engine for large-scale data processing back in the GBIF pipelines. Spark, however, is not suited to navigate relationships among records like the one needed to build an event hierarchy. We had to work with both an ad hoc implementation of graph frameworks and the use of an additional library called GraphX to overcome the limitations we found with Spark. As to the user interface, our first attempt didn't get us very far in the ALA, as the components were tightly coupled to the GBIF infrastructure. Fortunately, we could get past that in our second attempt. We are still working on improving this to have a pluggable system where, for example, the user interface can work irrespective of talking to the GBIF registry or the ALA collectory. Downloads is the area where we had to take different paths. For GBIF, enabling downloads for events was a matter of reusing its existing HBase and Hive infrastructure already used for occurrence records downloads. HBase is used to manage billions of occurrence records hosted by GBIF. For us in the ALA, the complexity of setting up an environment based on HBase was impermissible, as the volume of records we manage is a fraction of what GBIF does. We leveraged the existing infrastructure that we have, using Amazon EMR instead. In summary, the ALA is expanding its data model, adding support for event-based biodiversity data to allow the creation of richer statistical models not possible with occurrence-only data. We worked in collaboration with GBIF, leveraging on our combined expertise and aligning of processing as much as practical. We commissioned an end-to-end event-based system by extending the GBIF pipelines and creating a new user interface and download service. There were challenges along the way, such as competing priorities from both teams. In the technical space, to name one challenge, the Spark engine was not suited out of the box to manage hierarchical processing of data. This takes us to the end of the session. Ongoing collaboration has plenty of benefits, keeps building our social capital, and applies consistent approaches to common problems which benefits the rest of the community. For example, IDIC-Bio and the Living Atlases community can tap into this expertise. For ALA, the next step is to continue working to implement the new event system into production. This event system already backs the development of the new Australian Seed Bank online portal. For GBIF, this work will inform future development, particularly around the diversified data model. To finish, I'd like to thank the team that has made possible the work that I just presented. Thank you.
Thank you very much, Javier. Very good. Looks like there's been a lot of progress made with ALA and GBIF, and leading now into the addition of some work being done by IDIC-Bio to try to align all these systems. And Chris or Maureen, who wants to go first?
I'd also like to point out that there are a couple questions in the Q&A for the last two speakers. So down in the Zoom toolbar in the bottom left, the Q&A, you can type a response to those questions. Looks like they're directed at you. It might be better to type it than save it till the end.
Thank you, Jill. So Chris and Maureen.
Chris, do you want to go next?
Yeah, I can do.
Okay.
I don't actually have a video clip. I need to share my presentation.
So in the bottom Zoom webinar toolbar, there's a green share screen icon. If you click
Yes.
on that.
I have a system capture here. Okay, here you go.
Perfect.
I'm Chris Wilson with the ACES Lab. Today I'm going to talk specifically about the adaptation of the IDIG-Bio API to GBIF pipelines and their version of Elasticsearch. I'll discuss our reasons in general terms for moving to GBIF pipelines, the choice of adapting IDIG-Bio's API to pipelines instead of pipelines to IDIG-Bio standards. I'll discuss the requirements of adapting the search API to Elasticsearch 7. I'll cover the testing that will be carried out to confirm unchanged API behavior. And finally, I'll discuss the cutover methods that will be used to transition to the new code while maintaining continuous service. Unifying ingestion standards will mean that providers can expect their data to appear with consistent values between portals that use that standard. This takes away the burden of having to adjust data for each portal. Using GBIF pipelines should also reduce our burden of maintaining an entire ingestion code base so that our time can be used to add features to our portal. This is time better spent in data analysis, such as providing enhanced visualizations, machine learning applications, aggregations, time series animations, three-dimensional models, and similar features. Elasticsearch at IDIG-Bio is version 2 and utilizes types for search-based API functionality. Types have been deprecated in Elasticsearch 7, which is the pipeline standard. Types are most analogous to views in SQL and will be removed. The types we currently utilize will be combined within the master Elasticsearch index mapping. And this will yield equivalent functionality without the additional complication of supplying a type to the backend request. The IDIG-Bio API adaptation for pipelines will accept the exact IDIG-Bio API calls and return the identical responses as the current system. The change will occur on backend calls to Elasticsearch, and this renders the change transparent to end users and will not affect functioning code that uses our API. Testing will occur using our unit tests as well as with manual user testing. Our current API uses over 60 response confirmations and more than 100 expected value confirmations to verify nominal API functions after a code change. User testing will be used to identify any additional problems subsequent to user testing or to unit testing. Unit tests may be added to include functionality missed by automated testing. Maintaining continuous service during the transition will be achieved by following these steps in order. We will build an Elasticsearch 7 cluster that is production ready. We'll build production API or production ready API handlers previously tested. We'll configure these tested endpoints to use the new cluster, pause ingestion, populate production data within the cluster, atomically switch the proxy and SSL endpoints to search or to the search API, basically from the old to the new one, and finally restart ingestion. Modifying the pipelines project to support type-based Elasticsearch 2 would be more impactful on the code base, increasing the likelihood of having to fork the project. when a project is forked, new enhancements and bug fixes to the original project are more difficult to reintegrate. In the modification of the IDIC-Bio backend to accommodate pipelines, we support contributing to a common code base used by GBIF, ALA, and IDIC-Bio, and fostering cooperation between our groups. It will allow us more time to focus on providing services that the research community needs rather than duplicating services that are already near optimal. This concludes my presentation, and if you have any questions, I can take them now.
Are there specific questions for Chris? Or we can do them right at the end when we have a discussion. I think Javier is typing answers to his questions now, and maybe Fede is doing the same thing. So, Maureen, why don't we turn it over to you?
Okay, well, after all of those implementation details, I'm going to take a much higher level view of things. I'm going to play you my recording if I can find it. Share sound. Okay, looks like I'm gonna have to rejoin Zoom. I'll be right back.
Okay.
While we are waiting for Maureen, I think the two questions that were in the chat were answered, but if anyone else has any questions, feel free to raise your hand, or you can put a question into the Q&A. Since we've got this extra time right now, we can take any questions. Oh, nope, here's Maureen.
Did that work?
It looks like maybe we're looking at the wrong monitor. We're looking at a Zoom page.
Okay, let's try this again.
Yeah.
That's it.
Okay, good. All right, here we go. Hi, my name is Maureen Kelly. I'm a software developer at ASIS working for IDIC-Bio. I was hired back in February, and my main task is to work on our data ingestion code. I was planning to do a historical view of IDIC-Bio's code just in broad strokes with the intent of capturing the arc of its evolution, the pressures on it, and how it's changed in relation to those, and to show how our planned integration of GBIF's pipelines into our ingest process fits naturally into where we are now. This is going to be a case study for aligning systems, and it still is. In preparation for that topic, I did a review of all of our feature requests and bug fix tickets since 2011. There's about 5,000 of them. Not all of them had to be read through. However, it was gently suggested to me that while certainly of deep interest to me as a developer and inheritor of the code, the whole shape of the code story might not be of gripping interest to many other people. I had to admit there was a point to be had there. So I took a step out of the weeds and reflected on what I'd seen at a higher level. What I found was the story of a data center support team that was from time to time partially disassembled and reassembled again with new members, but always engaging with the technologies of the day, encountering common conundrums with thousands of other developers, and facing down the challenge of burgeoning complexity. This problem wasted no time presenting itself after the honeymoon was over, one that began with a clean slate of 0 lines of legacy code, 0 data sets ingested, and freshly installed hardware. But here I'll take, again, one more step back and look at the even bigger picture, which is relevant to systems alignment. We'll have a look at the hardware and software stack, not necessarily iDigBios in particular, but in general, the layers of technologies involved in running a data center and writing software applications, to see the nature of the beast. So by the nature of its delivery medium, software appears to emerge out of thin air. Ideas magically come into being and present themselves on your computer screen. And when well designed, the software provides a totally unsurprising response to something that otherwise exists only in your own mind, which is that what you expect to happen next. Some software is so good at this, it even seems to read your mind. But the smoothness of the user experience, of course, hides all of the details that we know are there. We all understand at some level there is more to it. Software is written and compiled and tested and installed and then served and so on and so forth, all behind the scenes. And that process, of course, does not run on ether. It must be tied to something that can, at minimum, count electronic pulses. And this is an image of a silicon wafer. And in truth, the silicon wafer level of the technology stack is a little lower than where ASIS is involved. But we will jump in on the next page. And in the meantime, I thought it made for a very pretty picture. That's why it's here. And to be controllable by humans, the varying voltages, of course, must be housed in something involving physical matter, like these servers. And those machines must be tended to, and their physical nature makes the tending to absolutely non-negotiable. It is a precondition for everything involving software. So few things grab a sysadmin's attention like a triggered temperature sensor. But the prospect of 7 to 15 inches of rain and tropical storm force winds arriving at the same time as this presentation is probably up there. So the trouble is, the machines need their own software, and tending to them requires its own software. And making sure that all the software is functioning requires more software. And every year, that software stack becomes deeper. Every time an abstraction is invented that can hide complexity, as a software library or other good IT tool does, it is possible to layer on even more complexity into your environment, because using that tool frees the cognitive space in your brain and your colleagues' brains. Not only is it possible to march on in this direction, perhaps not indefinitely, but certainly it marches on in this direction, it turns out to be economically inevitable. So there'll be more of it. Complexity will expand to fill its container, which in our case is the assemblage of brains of the iDigBio IT team. Interestingly, there are correlates to this principle in biological systems. A fundamental law seems to be at work. In this blog post, Mark Rubenstein, a former hedge fund investor, quotes Brian Arthur, a professor of economics, who in turn quotes Charles Darwin, who says that the enormous number of animals in the world depends on their varied structure and complexity. Hence, as the forms became complicated, they opened fresh means of adding to their complexity. The good news is that systems alignment reduces complexity. So as mentioned earlier, the iDigBio IT team encountered many of the same problems as other developers in entirely different fields. Every web developer who ever had to code against IE8 faced the same headaches. The same goes for software of a more limited developer audience. Biodiversity data aggregators. They encounter the same fundamental issues as well and explore the solution space to those problems either jointly or independently. The benefit of having many solutions tried is that an optimal solution is more likely to be found if in fact there is a single one, and having lots of solution options after that point has some downsides. As an example, the first computer language I was paid to write in was Perl. And Perl prides itself on its motto, there's more than one way to do it, and also in the arcana of its acronym, with its own pronunciation, Tim Toady. But even Perl developers, perhaps especially Perl developers, learn that a multiplicity of options is a powerful thing, but not always the best thing. Reducing the complexity of a software stack by using a common solution to a common problem is good both for me as a maintainer, it's also good for the collaborating maintainers. In effect, the collaboration increases the size of your IT team, which increases the amount of complexity they can handle. And it's also good for the software's user community because the reduced complexity frees up complexity brain space for using the to support the features that they want. And a fortunate data aggregator, one that has the enthusiasm of its user community behind it, will have no shortage of features for developers to work on. This is something else that I learned from my analysis of Redmine tickets. Aligning systems also frees the data provider from managing complexity imposed on them by different requirements for different aggregators of having to decide to aim for one particular data platform to the expense of another. And when publishing data in multiple places, having a uniform treatment of taxon names, for example, supports a uniform user experience at the output end of the process. And alignment has been happening in some capacity all along. There are a few tickets that I found in my review. iDigBio started using GBIF's IPT software back in 2014 to support smaller collections that couldn't run their own. And in 2020, not that long ago, GBIF ingested our collections catalog. And next up, we'll be adapting pipelines to our ingest process. So that is all. Thank you.
Thank you, Maureen. A global perspective indeed. So have we got, how many questions do we have in the chat? Do we have questions? So I have a question. And I should know the answer to this question. When you guys are all done, whenever that ever is, or even near done, does this mean that GBIF, ALA, and iDigBio will interpret and display the same record in the same way to all users? If that record appears in all three of those systems?
That is the goal, yes.
And you think that will happen?
I believe so, yes.
Fantastic.
Yeah, if I can take on that one also, Gil, I think precisely that takes me back 1 year ago, but presenting at TADWIC. Precisely, it is a slide that I have side by side with regards to the same interpretations run by the GBIF pipelines in GBIF and what we had also in the ALA. Exactly, I think that was spot on, and obviously it has been now more than a year that we have been running the pipelines, so I don't expect any different for iDigBio.
Right.
Yeah, there are some small differences there. That, for example, we have these flags for data issues so the set of flags that we use sometimes differ with the set of flags that ALA uses. For example, we have flags to say for to say that this coordinate it is in a different country than the one expected, and we have that's an example of multiple flags that we have in ALA. Usually, in some cases, uses a different set of flags. So the representation of the record is the same, but sometimes the quality the quality metrics and the assertions that we do in the data can differ. That's a difference in that if you analyze a record by record approach. Yeah.
So does that mean that the code for all three of these have to be in sync pretty much all of the time, or are you using the tools that help keep them in sync?
Ideally, will be at least the fundamental, let's say, the record quality measures should be in sync. I mean, I don't think that we should enforce. I mean, all the platforms to use the same quality metrics. I mean, IDIC Bio can come up with some new set of metrics, maybe a new set of assertions from the base, and the technology stack in the same for ALA. So
that could benefit all. I mean, if anybody comes up with a new innovation that helps, other people can adopt that innovation as part of the code or part of the tools they're using.
What we're trying to do in the GBIF pipelines is that when we see something that is sensible in ALA, we try to actually port back that in the implementation to the pipelines as part of the core components. So, for example, if IDIC Bio discovers, let's say, a new way of interpreting data, or for a new data session that worth having the core components, I think we're more than keen of moving that into the core components. Or, for example, if we need one field more in a specific interpretation, we're more than keen of adding that into the core components.
Right.
Yeah.
And Gail, I wanted to make sure, Yuta in the chat asked, what are your thoughts on a digital object architecture approach? And it was to all speakers, so if anyone would like to address.
I have not much background about the digital object identifying. Yeah, but my understanding is that it's kind of a black box where you basically pack some data there and you assign an identifier. But my concern about that is whatever is in that box, if we're talking about the same specification, it is up to the implementation to decide, and that is the standardization part that concerns me a little bit. But yeah, but I don't think that I have enough background to have an educated opinion about the entire architecture around that. Yeah.
Okay, thank you very much. I'm afraid we're going to have to stop because the other folks are showing up for the next session. But I do want to make one point that Jose Fortes made in the chat. He says the goal is consistent content, but possibly different presentations and different applications. That sound reasonable?
Mm-hmm. Yeah.
Okay. I want to thank you guys for doing this. I know you're working hard on all of this, and I think it's very impressive. And I think it's going to be of real benefit to the global biodiversity community, biodiversity data community, for all three of you, which are part of leading aggregators, to really work together and build a system that does provide fairly consistent data across all platforms. And I think that's very exciting. So thank you very much for being here and for presenting this. I really do appreciate it very much.
Thank you.
Good.
Thank
Thanks,
you.
everyone. Thanks for organizing. Bye.
Okay, up next, for our last discussion group in room 1 today, we have including indigenous metadata in collection records with Maui Hudson from the University of Waikato. I'm sure he will say it better when it's our turn. Sorry about that. And Jane Anderson from New York University. Thank you both so much for being here. I know this is something that people have had a lot of interest in, so I really appreciate really appreciate you all being here. And just as a reminder, we'll be using the Q&A in the bottom tab of your Zoom, my brain is frat toolbar at the bottom of your screen. I've only said it 10 times today. In the bottom toolbar there, folks in the audience, you can either raise your hand or put questions directly into the Q&A. But I will pass it over to you all to take from here, and I will be here in the background if you need me. Thank you both very much.
Gillian, thanks very much. Kia ora koutou katoa. Mahina ki koutou tēnei ahi. My name is Hudson. I'm based at the University of Waikato down here in Aotearoa, New Zealand, and really looking forward to be a part of this session. I hope you can hold along. Didn't mean to stop the flow of the last conversation, but I think there's definitely some elements that we'll be talking about which can align. We're really interested in that sort of alignment of data as it moves into different places. So, Jane.
Great. Hello, everyone, and thank you so much for joining us and for the invitation to be here today. I'm joining from Lenapehoking, the lands of the Lenape nations in New York City. I would begin by just offering my respects and acknowledging the elders and the ancestors of these lands and waters who continue to steward them, as well as all the relatives that are around these spaces as well. So we've got a PowerPoint that we're going to share with you today. Maui's going to do that. And we'll kind of then just jump in. Please do write your questions in the Q&A or in the chat. And Maui, you take it away.
Sure. Yeah, so title here, including Indigenous metadata and collections records. I think that's one of the elements that's come about in part through the sort of larger discourse that's been happening around Indigenous data sovereignty, or thinking about how to enhance Indigenous control of Indigenous data. And this is a discourse that's really one that's thinking about what sorts of rights and interests do different parties have as data becomes more mobile and is shared in a lot more, a number of different sort of forum. But this arises from kind of thinking around treaty rights or cultural intellectual property rights, Indigenous research ethics, and has these two sort of components, one about data for governance, which is primarily around thinking about issues of access, whether people can access data to help them make decisions about the places they're from. And the other one about governance of data. So as data becomes more open and available to everyone, what are the situations where some kind of governance is required? These sorts of discussions have been led towards the development of the care principles, knowing that most data sits in other people's repositories where other people have that stewardship or governance responsibility for it. So how do Indigenous peoples participate in that? In some ways, the care principles are a little bit of a counterpoint to the FAIR principles. So where the FAIR principles are focusing on the data itself and the characteristics of the data to make it easier to share and link and reuse, the care principles are focused primarily on the people and the purpose of its use. And so these ideas around collective benefit, authority, control, responsibility, and ethics being considered as a complementary set of principles alongside the FAIR principles. And that's something that's being promoted by places like the Research Data Alliance. So we talk about, data can be fair and care. Jane.
Yeah, sure. Let me take over. So we're just kind of thinking about the kind of data and information infrastructure challenges, and the project that we're going to talk to you about today, the local context and the intervention that we've developed through digital tagging of using labels and notices, really responds to these kind of 5 key issues. The first is that every Indigenous community has enormous collections and data held in archives, museums, libraries, repositories, and other online databases, and that within these collections, there's significant information missing, not only individual and community names, but actually proper provenance. And that information is missing and makes it very difficult to use into the future, or also to allow for Indigenous communities to actually benefit from that use and have decision-making control over that. One of the other areas is that Indigenous peoples and communities are largely not the legal rights holders of these collections and data, and this also means that they have limited capacity to make decisions or have any kind of control over those collections and data into the future. What that means is that these issues of responsibility and ownership, as well as the kind of incomplete and significant mistakes in the metadata, actually continue into the digital lives of this material. And so whilst this is already existing problem and particularly pervasive within historical collections, there are actually more and more researchers working and collecting information from Indigenous communities. And because many of these research practices in terms of inclusive metadata are not yet part of how researchers necessarily do their work with Indigenous communities, these particular problems persist in the creation of new data and of new collections. So just kind of like restating some of these problems in different kinds of ways. One of these, there's kind of three key ones. This particular problem that we've been thinking about now for many, many years is really arises from the histories of documenting Indigenous peoples and communities. And that's so not only kind of documenting Indigenous cultural practices, but also documenting Indigenous knowledge around plants and particular species. This is just an example of some of the work that we're doing with the Academy of Natural Sciences in Philadelphia around the Lewis and Clark expedition. Lewis collected multiple plant samples as throughout that kind of expedition, which also included information and native knowledge about those particular specimens. And so kind of what our historical collections are dealing with is kind of this particular focus on Indigenous people as a particular subjects of study, but not necessarily having control or decision making or even knowing where their collections are, which leads us to this second problem, is that it's very difficult to govern Indigenous data if you can't actually find it. Because of the missing information that sits within these collections, missing Indigenous names, communities have a lot of difficulty in actually finding that material in the first place. So one of the kind of interventions that we're trying and offering up to kind of think through today is what happens when inclusive metadata is part of a different kind of process, and there's also a disclosure of Indigenous rights and interests as kind of part of a mechanism that actually makes that data visible in the first place and actually contributes to making it findable into the future. The third issue that we have is a kind of a standard intellectual property problem, one that kind of continues to haunt Indigenous collections, wherein Indigenous communities are not the legal rights holders over their information or their data in the first place. So whilst many people can use traditional intellectual property law or different kinds of licenses around collections and data, Indigenous communities have been kind of left out of that system through different kinds of colonial processes in the operation of the law itself. So one of the strategies that we've developed, kind of understanding that there are different parties with different kinds of interests within this space. We have particular interests that Indigenous communities have, but also we have interests that researchers and institutions have in terms of kind of making visible Indigenous collections in the first instance, but also creating capacity for Indigenous peoples to be part of decision-making around how those collections get utilized into the future. So we have the kind of a mechanism that we call the notices, which are kind of digital identifiers which work to kind of disclose Indigenous rights and interests, not only at the kind of level of there are Indigenous collections within this institution, but also kind of marking instances where the metadata might be incomplete, attribution might be incomplete, but also that the collections might hold traditional knowledge on one hand or biocultural information from Indigenous Indigenous communities on the other. So we have 4 notices that we really encourage institutions and researchers to utilize as part of marking a new ethics in engaging with Indigenous collections that might be held within certain kinds of institutions and data repositories. Just going to give you a couple of examples of notices within this being utilized within this space. So this is an example within a kind of more traditional knowledge collection of photographs within Simon Fraser University. This kind of open to collaborate notice, which is being utilized to indicate that the George and Joanne MacDonald Northwest Coast Image Archive is actually entering into a process of going through and updating their photographs by including Indigenous names and Indigenous community names, so that any future researcher knows whose information they're actually utilizing and can actually reach out back to those communities to actually engage in partnerships and relationships around using those images into the future. This is an example of the notices within a genomic database called Geome. Again, that first starting point, that kind of low bar of engagement, is really around the open to collaborate notice, which then kind of activates a process of engaging with communities.
And this is the first sort of working example of a bicultural notice being put on some genomic data. So this is the GDV database. This was put in place for the bilberry, and the bilberry is sort of a native blueberry in Scandinavia. Just happened to be sequenced by a research team based in Aotearoa that had been part of our conversations around the development of the bicultural labels. And so they've applied the BC notice to this data set.
And this is an example of kind of where this starts to go. This starts to also move into different kinds of publishing contexts, different kinds of disclosure of engagement with Indigenous communities. This is obviously the in the global plants in JSTOR for those plant specimens that I was speaking about before from the Academy of Natural Sciences. But it kind of leads into a way of thinking about different kinds of ethics and different kinds of disclosure, particularly in publishing context, where researchers are actually working with Indigenous communities. They want to actually make that relationship visible, because it actually changes how people understand how the research is being done in the first place. So the tool that we have then developed for Indigenous communities are something that we call the traditional knowledge labels. And this is kind of one. I'm going to talk about the traditional knowledge labels, and now he's going to talk about the biocultural labels. The traditional knowledge labels were developed as part of this effort to really think about what does it mean to create a different kind of system where Indigenous rights and interests and protocols around using particular kinds of material are actually visible within digital infrastructures. What would it look like to do that? And so, working in partnership with Indigenous communities across multiple countries, we developed a suite called Traditional Knowledge Labels, which really allow for different kinds of expressions of interest to actually stay with collections and data as that travels across different digital infrastructures. So there are 20 traditional knowledge labels. I'm not really going to go into them in a lot of detail, because we're going to kind of stay with some of the biocultural labels as our kind of primary examples. But just to say that one of the primary labels that gets used by every community is the attribution label. The attribution label allows for community names to actually be present within the record in a way that they previously were not possible. This is an example of the attribution label that was developed by First Nations community in what's currently known as British Columbia, Canada, the Scowlitz band of the Stolo First Nation. And in this example, the attribution label is kind of referring really specifically to a particular community. And what's unique about the TK labels is that every community has the sovereign right to define the terms of that label. And so here you'll see an example of how the Scowlets have customized this label to really kind of speak to histories of exclusion, histories of erasure, and futures where the Scowlets want to be part of research and engagement and partnership.
And so we also developed a set of labels for the biocultural labels. Now they came in part from the background which I'd had around developing ethical guidelines for genomic research with Māori and also with Indigenous flora and fauna for Indigenous communities here in New Zealand. Seeing the sorts of expectations and protocols which those communities had, and then getting involved in the discussions around Indigenous data sovereignty. When I was introduced to the traditional knowledge labels, could see that they had a potential application around not only the traditional knowledge elements which you would associate with genetic resources, but the data generated from the genetic resources themselves. And so here we have a set of biocultural labels developed in collaboration with communities, but also scientists that were interested in ensuring that the interests of the communities that they worked with could be maintained into the future. In lots of instances, researchers are working with communities for conservation or biodiversity purposes. They don't have a focus around any kind of commercial applications, but the data which they generate, which is then pushed into open data platforms, then becomes available for other people. And somewhere in the mix of that transfer of information from a community context or a local project context into the big wide world creates some of the concerns for communities around appropriation. And so the ability to maintain their name and their the sorts of relationships which they would like to maintain with that material into future collaborations can be reflected on the record. And so here we have a similar sort of set of labels which can be applied more to the scientific data that's been generated from Indigenous territories. And here's an example of the Provenance Label. Provenance Label is very similar to what we just talked about, or Jane just talked about with the TK labels in terms of attribution. So really just affirming the interest of the community and the material and data about biodiversity found on their lands, territories and waters, and retaining the right to be named and associated with that material into the future.
So what the labels really communicate are three clear things. And I think it's important to also say that the labels are developed, with a nod to Creative Commons, understanding that the Creative Commons created a particular set of licenses that were both human readable and machine readable. What you're seeing here with the icons is the human readability component of what the labels do. The labels also have permanent identifiers when they're generated by communities, and we'll kind of talk a little bit about that with some of the examples that we have for you. But the three things that the labels really communicate is provenance. Where has this information and data come from? And kind of what are the different responsibilities and relationships that sit behind that? They communicate community protocols for viewing, for sharing, and kind of making sure that those already existing community rules are also part of the kind of data systems moving forward. And then they also communicate permissions. What kinds of permissions and consents have been granted? What kinds of engagement have existed with communities and researchers? And what kinds of future possibilities exist for using particular kinds of information as well? So I'll just give you the first example. I think we have four for you. This first one is with Geome. I kind of mentioned Geome before. Geome is a genomic metadata database. And they started off utilizing the Open to Collaborate notice that you can see in the bottom corner. It clicks to open to kind of say this is kind of what Geome is committed to as a metadata database in relationship to the kind of information that will be stored within the database. what they have now done, and John Deck is kind of one of our collaborators in the local context space as well, is kind of thinking through how the geome database speaks back to our local context, which generates both the labels, notices, and allows meaning of here you'll kind of see, and this is kind of what has been mocked up within the geome system to start with, is kind of in the project. If you kind of click on the project, you will kind of then be taken to a table where you will kind of find the list of samples. In the list of samples, if you click on one of these samples, it will start to show the labels, so that the labels are actually connected to the sample, both with the material sample ID, but also with the event ID as well. So it can the labels can be shown not only on the sample itself, but on the overall project. Remembering that the labels are coming directly from the community itself, and this is kind of an important relationship that sits between engaging with communities and institutions and researchers, really utilizing the notices as their kind of first point of disclosure, that then communities then engage with and add these particular labels around the sample or around the overall project itself.
And so, so while that application is in development, and it's been a sort of a mock-up to show what John Deck's intending to do in the context of geome, and that sort of work is underway. This example, which I'm going to show now in relation to Manaaki Whenua or land care research here in New Zealand, is actually live. So you can go to the systematics data collection, and this is their new platform as they've tried to make their data more available and accessible to the public. If you go into their systematics data collection website portal, in this instance, you can just put a star in the top box, and this holds 667,867 records primarily across 4 different collections. Just wanted to highlight here too, on the left-hand side, and the spaces where you can filter by a range of different things, the type of the species, the genus, the country where things are happening, but also they've added in the native lands sort of application. So native lands is a particular website with a portal which shows a range of kind of geospatial areas associated with traditional communities, something which is they're always looking to improve, but based on a lot of information that's publicly available, including the ones in New Zealand. So this database itself has these over 600,000 records, and if you go into the list view on that and click on any of the items, you'll see that they've added bicultural notices to each of those. And so those notices are just, as we've talked about earlier, indicating that there are these interests that sit there in relation to that record. So they've also been working directly with Whakatohia, which is our community, and you can see you can either use the native lands plugin to find Whakatohia or do the shortcut, which I've put up there. And so when that's searched with that term with our community name, we end up with 1,203 records, for which they then created a specific project for our community on the local context hub. And so this is the local context hub. We're both the community, and so this is our Te Whakatohia account, which has projects, and those projects can be either developed by ourselves or by other communities. And Manaaki Whenua has their own account, and they created this project called the Biological Specimens Housed at Manaaki Whenua, Te Rohe o Te Whakatohia. That was sent across to our site with a bicultural notice on it, and then we had the ability to apply labels. So We chose the labels which you can see selected there. The provenance label reflecting the connection to our territory. The research use label saying we're fine for this information to be used for research purposes. And then the open to collaboration and open to commercialization labels. So just letting future users know that even though it's fine to use it for research purposes, we're happy for them to contact us and become engage in collaborative research efforts. And so once we applied the labels within the local context hub, they use the API to then add our labels to each of the 1,200 records that sit on the Manaaki Whenua database. So this is the first example we have of kind of live use of the local context hub, use of the API to drop labels onto an active system.
So as would kind of be evident from like what Maui was just talking about, we have all these different projects where we've kind of been testing the labels and understanding the different kinds of implementation stages that are required, particularly for a project like this in scale. So when we began doing this work within kind of cultural heritage collections, we were dealing largely with, 10 to 20 different kinds of items, for instance, photographs or sound recordings or something like that, which is part of our, our Library of Congress example, which we didn't use in this context today. But what has kind of happened since then, particularly around the biocultural labels, is like really working out how to do this work on 670,000 records, for instance, and kind of what does that mean to do that, and kind of what is the workflow for that kind of enables it. So this is another project that we've been working on with the University of Maine and Maine eDNA with Andy, Darren, Beth, Jennifer, Melissa, Kimball, and Laura Jackson. And so in this project, we're kind of getting at a little bit of a different kind of problem, which is really how do researchers in the very first instance when they're in the field actually mark that they're on Indigenous lands and waters as kind of part of their initial data collection. What Maine eDNA started with was, again, using the Open to Collaborate notice, which kind of made visible the Maine EPSCoR's actual commitment and framework around ethical research to actually be doing this work in the first instance. This notice was also added because there had been kind of collaboration with some of the tribal communities in Maine, which is Wabanaki homelands. So this kind of like open collaborate notice then kind of began a process, or was kind of part of a process that then the team at Maine eDNA kind of started to initiate, to kind of think about what are the workflows that are going to be required to make sure that any kinds of notices and labels that are added by the Wabanaki nations can actually be included in the systems as that data travels through, and kind of what that looks like. So this is just the field sampling survey that they've kind of, for survey 123, that they're kind of utilizing as that first instrument for data collection. And again, kind of making that notice visible within that for the different researchers. And then this is the kind of entity relationship diagram, the different kinds of phases of research, as well as kind of where the data will start to go. And so where we've all connected into is through the different project post the field survey, which then connects to the local context project ID in the local context system that Maui was showing you a little earlier. And again, this kind of speaks to the different movements from kind of laboratory to different kinds of metadata, and then into different kinds of systems themselves.
And so, one of the things that's been fortunate to do is work with different groups that are interested in, really addressing their sort of challenge of recognizing Indigenous rights and interests in this sort of material, and thinking about what does it mean to sort of embed it within their systems, what kind of space can be made to ensure that that the conversations, that the information, that the provenance information is sort of retained and maintained as the data moves in and out through their systems. So one of the other places we've been working with is a European Reference Genome Atlas, alongside the people that are listed there. They're creating reference genome sequences for European species. But there's interest, there's also interest from Europe and, a number of other places, because even if they're often working with material that comes from other countries and those countries that have Indigenous peoples in them as well. So as they've been creating this reference tool for conservation and management, sorry, they've been thinking about how to create a pan-European genomics infrastructure that can support genomics for all the European species. And a big part of that has been thinking about how they unlock the power of the metadata. So I think that all the sort of things that were happening in the last session around a sort of alignment, where things sit, what sort of information is required around basic information, provenance, attribution, but also there's these ideas around ownership and rights. And you'll see there that it talks about ABS permits, so access and benefit sharing. This is where it starts to link back into the Nagoya Protocol and the Convention on Biological Diversity. We know that there's the COP15 Conference of Parties coming up in Montreal in December. And one of the big issues on the table is the degree to which digital sequence information should be included in the benefit sharing arrangements. But here you're also thinking about access and use. And you can see that they're starting to give some consideration to not only how the information about the samples and sequence information is being managed in a way consistent with the FAIR principles, but they're also starting to give consideration to the care principles as well. And so one of the things that they've been, really looking at is, or developing, has been their metadata manifest to put together standard operating procedures, thinking about what sorts of ethics permits and species collection permits CITES need to be included within the information that's collected, and have now included within that metadata manifest information, or the labels themselves, but also some other space for additional information. And I think that that's an important thing to keep in mind, is that there's certain amounts of information that can be captured within the labels themselves, but it doesn't necessarily capture all of the Indigenous metadata that's necessary to make the system responsive to the sorts of future needs that people might have. And so the thing that they've been doing is then thinking about what does that workflow look like from the information provided in the metadata manifest through their other systems. Now this is kind of gets way over my head. I'm sure a bunch of you guys would kind of understand what's been reflected in this this slide, but essentially, working through the metadata broker, how that information gets into the URGA data portal, where requests can be made, and different sorts of information either end up in the URGA data repository or within the European Nucleotide Archive.
And so then our last example, or kind of who we've been working with to think through the different kinds of fields that the labels and the notices go into, is with DataCite and thinking about kind of DataCite integration. So we had a workshop with DataCite and I think 8 different repositories within Canada, thinking about what the preferred approach for DataCite is, with kind of text description and attributes for both the notices and the labels. So this is kind of what the recommendation is that's now coming from DataCite, which is really kind of utilizing the field of rights, and rights identifier is kind of the place for where the notices and the labels are placed. This is just an example of what the notice would look like. And then that has led to guidelines from DataCite in relationship to integrating the local context notices and labels. And so some of these examples that we have, we're happy to put in the chat for you after this so that you have them and kind of can spend some time with them yourself.
And so just that's people coming in saying hello, Peabody. Anyway, so just sort of kind of coming back a little bit full circle and thinking about Indigenous data sovereignty and sort of, enhancing Indigenous control of Indigenous data. But what you get a flavor for from, our work with communities around the notices is really this desire for acknowledgement. As information and as data and as material is taken from those communities and becomes shared within the world, that it's important to acknowledge that contribution, and then how that acknowledgement then starts to move through into some form of attribution, which becomes more formalized, and whether or not that translates into the space where authorship's required. And so in some places, there's journals that are emerging which won't publish Indigenous content now without Indigenous authorship. So I think the labels play a part, particularly in maintaining that sort of acknowledgement and attribution, at least within the records. And so if we can have that maintained in the records in a more consistent manner, just like rights holders normally have, how authors, researchers get cited as their publications get reused, maintaining that Indigenous name, those Indigenous interests within this our system as that happens is a really important feature. And when that name is there, that relationship's in place, they can get into different sorts of discussions about what the nature of access looks like. And while most of the data is sitting in open access formats, there is definitely places, even outside of Indigenous context, where access is managed, maybe by the researcher, maybe by the institution. Requests need to be made before it can be, the data itself can be shared. And so those things, I think, are important to think about in the mix of this conversation as well. And a big part of it is really trying to ensure that some authority is maintained, or ability to exercise authority is maintained by those communities, particularly in the transition from sort of public good uses into commercial uses. And that becomes much harder to manage in an open data environment if that provenance information isn't readily accessible and transparent. So I'll say thanks very much. I know we got a bit of time left for questions, which we're happy to answer. If people have got want to get in touch, this is Janet Hamilton-Pierce, our program lead. She'll respond to any kind of requests at our support@localcontext.org email. And we have a number of working groups that are helping us move this initiative forward as well. So, Kilda, thank you very much.
That was great. Thank you both so much. Yeah, we've got a couple questions in the Q&A. And then there's also, I guess, more of a comment from Harpo Faust in the chat, but there are a couple of questions in the Q&A.
I can see that first one from Jutta. I think Maui, you might be able to speak to that, particularly with the most recent kind of example with Whakatohea and Manaki Whenua.
Yeah, so it's and part it's probably going to vary depending on the different sorts of context. So, if you look at the main eDNA example where they're trying to integrate the use or the application of the labels as a part of the collection process, it may become a little bit more fine-grained. What we've been conscious of is trying to introduce something like this into infrastructures which have been developed over a long period of time. There's a lot of labor required to do that. And so we've been thinking and also working alongside different collaborators around trying to do that in the most efficient manner. So with Manaaki Whenua, what they did was created a sort of a project that covered the entire collection. And so that's one that allowed the sort of biocultural notice to be applied. And so the project is the one which has the ID. So all of the records have the same ID associated with it. When communities come to them and say, hey, look, we're interested in thinking about what sort of labels we can apply with the samples that relate to our community, then he's created another project that just relates to all of the samples within that area. And because he knows which of the samples sit within those sorts of boundaries, he created another another local context project, which means that all of the items that sit within there share a new ID, and then that ID can then be linked to our labels, and that's how we've been able to add our sort of general set of labels to those 1,200 items. Our sort of thinking from the community point of view is most of those items will have the same expectations or protocols around them, unless you're dealing with something that is maybe like a totem or a really significant species for us. And then around those ones, we might want to create a different sort of project just to create a different sort of ID so that we can be more fine-grained in terms of how we would deal with them. So it's a little bit of I would say a bit of a both and situation.
And then just in relationship to that second question there about decision making and whether there are multiple groups that might have an interest, certainly yes, species don't necessarily contain themselves to one tribal nation location. And one of the things within the main eDNA work that we have been doing is kind of, well, so first of all, we have labels that reflect multiple community interests in the first instance, so that somebody would know that there are multiple community interests that sit there. But what we've kind of done within the main eDNA work is actually, because we know all the communities and all the communities are kind of relatively identifiable within that particular context, we've had conversations with the tribal historic preservation officers about how they want to be alerted to particular kinds of sampling or specimens that might come from their lands and waters, particularly if there are particular concerns that might exist around where some of those samples were taken, for instance, where there might be burial mounds or ancestors that have kind of coming in those particular kinds of spaces. So we work to develop a system of where all the typos in this instance, for example, are part of a conversation about how they want to be associated with those samples and specimens, and which community actually has authority over that, and which community actually has overlapping interests, but not in that kind of there is a tribal authority that sits there in relationship to it. Certainly, in the way in which the labels are designed are that the information about who added a label is part of the project ID. So that kind of also makes it clearer in relationship to who has been actually adding that label in the first instance.
So if I just add a couple of points to that too, let me, I'm going to share my screen and sort of hopefully answer this in a live way. So this is I just wanted to show here. So this is the 1,200 records that Whakatohia set in place. And so one of the things that happens is it's not just, it's the areas reflected in native lands aren't sort of boundaries, so they're not hard, and they often have sort of overlapping areas. So one community is saying, here's the area which we have an interest from, but it may overlap with others. So in this instance, there's these 1,200 records that show up under Whakatohia. But if I go down to the native lands module here, just on the left-hand side, you might be able to see that there's got Whakatoa here, 1202, and then Tuhoe, which is our neighboring, one of the neighboring tribes, is 288, and Ngāti Awa 149. So that's actually saying out of that 1200, 149 of them are also within the area which Ngāti Awa has sort of interest in as well. So we can, there's a, and if we go to sort of have a look at that, not only is the labels sitting there, which are the ones that have been put on by Whakatoa here, but there's still the biocultural notice shown, which is, you know, sort of indicating that there's potentially other interests that would sit there as well. Now, we know that part of what we have to think about in the future is, you know, what does it look like when we have different sets of labels from different communities that sit there. I think it's fine that they may be at odds with each other in the sense that some communities might be comfortable with commercialization and other ones won't be. But that would really just inform the sorts of places where people would be, would likely start their conversations. And some of the internal relationships that we have between communities, you know, we deal with some of those things ourselves.
I don't see any other questions. Give folks another minute, but again, thank you both so much for being here. That was great.
So do feel free to reach out to us or to Jeanette. Oh, I should put the site in the chat as well, right?
That would be great. Thank you.
Yeah, and so there's, you know, there's it's definitely a bit of a work in progress. Like we're really, you know, I think from a community point of view, there's been a lot of, you know, there's sort of 10, 12 years of engagement with communities in the development of the traditional knowledge labels. And then, you know, over the last 3 or 4 in the application of the biocultural labels. It's really the sort of technical side of it and working out the different ways in which it can be integrated into workflows. And so as they're emerging with some of the groups that we've talked about, really interested in making them available for other groups so that it can be integrated more widely across, you know, I guess, data ecosystems. Oh, I see there is your work transferable to other data portals. Yeah, I think that, you know, this ends up being, you know, the big question is the degree to which some of the work which, say, Manaki Whenua has done to integrate the labels into onto their system can be informed or just be used in other places. We're hoping to kind of be in a position to collate those examples to make it easier for new users to think about applications onto their systems too.
Thank you so much. I think my toddler is about to break through the door, so I think I'm going to go ahead and wrap this up. Thank you both so much, and thank you to all of our speakers today. We'll be back again tomorrow for workshops. Yes, thank you both so much, and thank you everyone for a great day.
Great. Thank you so much, everyone.